Yeah, 7.4. Let's make a family tree. Perpendicular. I meant to say properties. Properties are special parallelograms. Let's make a family tree, why don't you? So I'm gonna draw. Oh my god, that is such not. Alright. Anywhoosie, this is a parallelogram. Today we're gonna be learning about them and all of its fellow friends that go along with parallelograms. One thing that we need to know about parallelograms is the fact that the special trait that makes a parallelogram is opposite sides being parallel. Any quadrilateral will have this. Well, any quadrilateral that has opposite sides parallel is a parallelogram. This is the defining trait of a parallelogram. And what I want to take from this, we're going to expand on this defining trait into two separate entities, one being rectangles and one being rhombuses. And we'll write rectangles and rhombuses. Rhombuses. So, we're going to take this, opposite sides parallel, we're going to expand on it, going into two different subcategories of shapes that are still parallelograms. Those being rectangles, those being rhombuses. Now, the reason why we have a split is because these two shapes have different specific properties that only work for rectangles and specific properties that only work for rhombuses, which is why we have the split. One other shape I want you to consider is a square. Squares. Okay, squares. Now, where does the square fit in this little diorama? Well, it's kind of the combination of both a rectangle and a rhombus when we talk about the special traits. Now, I know I said this is a family tree, but it's definitely not treeing out. It's definitely more circly. But besides the point, what I want you to take away from this is that these are still all parallelograms and that they all have opposite sides parallel with each other. Opposite sides parallel. All of these shapes have opposite sides parallel. And I'm going to draw each and every one of these arrows in green. There we go. This is true for all of them. Every single one. Now, what is the difference between a rectangle and a rhombus, though? Why are they different? Well, that's what we'll do right now. We'll figure it out. One thing we'll do first is talk about rectangles. We kind of did rectangle stuff already in the time we had to measure out objects in class. That's when we saw rectangles the most and saw a bunch of properties that dealt with rectangles. One of those properties being, one, opposite sides parallel. Second, we have opposite sides congruent with each other. So that means we have opposite sides congruent with each other, just like opposite sides parallel with each other. Cool. Another thing we noticed is that all angles were 90 degrees. So all of our angles that we measured were 90 degrees. That's another thing that we noticed. a second thing, or a third thing. We had diagonals intersecting. Same length. A lot of us measured the same length when we were looking at the diagonals in the shapes that we had. Most of our rectangles had diagonals that were the same length as well. And all of the properties with parallelograms that we've had already, the ones that I haven't mentioned, like opposite angles, congruent, like that stuff, still applies to rectangles because it's a parallelogram still. Every property from a parallelogram still applies to here. So everything from 7.2 and 7.3 still applies to rectangles. And that also applies to rhombuses. The thing that I want you guys to take away, and it's going to be building off of this one right here, is that when we have rectangles and we want to talk about its special property, its defining feature, it is that we have all angles congruent to each other. This is the special defining trait of a rectangle, and it's basically a rewording of what we already said and what you guys noticed already when you were measuring, is that all the angles were 90 degrees for a rectangle. So that's the defining trait of the rectangle. If we have a shape that has all angles congruent with each other, then it's going to be a rectangle. I know what you're thinking already, and you're looking at this little box right here, but we're going to not talk about the box right now. We will wait on the square. Rhombuses. I will choose blue. Rhombuses still hold all the same properties for shapes. They have the same properties as parallelograms. Still, everything that applied up here for this shape right here, that's a parallelogram, moves down here. So like this would apply. Diagonals intersecting, that would apply. Same length, not always. Not always. Specific cases. And we can talk about that specific case when we talk about the square. But we're getting ahead of ourselves. One thing to know also is opposite angles are congruent. Not all angles are 90 degrees on a rhombus. Consider these two rhombuses right here. These are definitely not 90 degrees. This one is definitely different from this one. These angles are definitely not 90 degrees. We can make an argument on this one because it kind of looks like 90 degrees, but we also just don't know it because it doesn't say it's 90 degrees. But not all rhombuses are 90 degrees, so we can't say this is true. But in similar vein of saying that all angles are congruent on a rectangle, we can kind of say a similar statement with the rhombuses. Its defining feature is that we have all sides being congruent with each other. This is the defining trait of a rhombus. So that means all sides on these shapes are going to be the same length. They are going to be congruent with each other, which is why we see the shifts in the angles. The opposite angles are going to be congruent with each other. That's why that is true. Now, taking a look at that and kind of thinking it over a little bit, I guess, you can kind of piece together why squares are a combination of both rhombuses and rectangles. Because squares take those special properties of rectangles and rhombuses. They are the combination of special traits that rectangles and rhombuses have. The one for rectangles being all angles congruent. And the one for rhombuses being all sides congruent. That all applies to squares. With these two things in one shape, that creates the square. And just remember, all the properties from a parallelogram from 7.2 and 7.3 still apply to these shapes. Maybe that's something we can write in the recap. All parallelogram properties from 7.2 and 7.3 apply to squares, rhombuses, and rectangles. It's a good thing to know because it is true. So, we know a lot about rectangles already, but we don't know too much about rhombuses. So that's what the next few theorems go with. They're rhombus theorems, one being with its diagonal, one being with angles. So 7.11, the rhombus diagonals theorem, it states that a parallelogram is a rhombus if and only if its diagonals are perpendicular. Remember that perpendicular means creating a 90-degree angle. So looking at our picture right here, we can say that ABCD is a rhombus if and only if segment AC is perpendicular to segment BD. Now this arrow going back and forth, that means if and only if. So if we have these segments being perpendicular with each other, then ABCD is a rhombus. If we are given the statement that ABC is a rhombus, then its diagonals are going to have to be perpendicular with each other. It goes both ways. It has to be intertwined with each other. That's how an if and only if statement works. Like so, or furthermore, 7.12 is also an if and only if statement, saying that if a parallelogram is a rhombus, then, well, if it's a parallelogram is a rhombus, if and only if each diagonal bisects a pair of opposite angles. So, looking at our picture, hold on. I will color AC green, and I'll color BD red. So, ABCD is a rhombus if and only if two things are met. if these two conditions are met, then it's going to be a rhombus. 1. That segment AC bisects the angle DAB and angle DCB. So the green line bisects these two lines, or these two angles. That's what it's bisecting. And that segment BD bisects angle ABC and angle ADC. So our red line BD, it has to bisect the angle ABC and ADC. Very clustered right there. But if these two conditions are met, then it's going to be a rhombus. If we are given a rhombus already, then these two statements have to be true. Using these two statements, we can find the measure of the numbered angles in the rhombus given to us, and we can also state how we found them. So the numbered angles that we want is the measurement for angle 1, 2, 3, and 4. This is what we're trying to find. And I want to know how we found them with one of our theorems and the actual value of it. So let's work down the page, or work down in order. So angle 1, it's in this intersection right here in the cross zone with the diagonals. Using our theorem about rhombus diagonals, the diagonals are going to be perpendicular. So that means that's going to be 90 degrees. So I can say angle 1 is going to be 90 degrees because my diagonals are perpendicular. So, okay, that's angle 1. Angle 2 and angle 3. This works with these two up here by angle A. And I see at angle C, I am given 61. So, remembering just properties of parallelograms, because remember, rhombuses are parallelograms, opposite angles are congruent. This works out in my favor. Also, that looking in our picture right here for 7-2, we have congruent marks with our bisection. So we have two little angles that are congruent right here and two little angles that are congruent up here. So the bisection splits the big angle into two congruent halves. I can use that to my advantage for 2 and 3. If I know that this is 61 right here, I can say for both angle 2 and angle 3, that's going to be 61 degrees. Because of opposite angles theorem, or opposite angles congruent theorem. If you want to be specific, you can say rhombus congruent theorem, but I'm okay with you saying opposite angles theorem. Or opposite angles congruent, not theorem. Say congruent. Congruent, not theorem. So that's 3 out of the 4 that we need to find. Angle 4, we can find this 2 ways. I'm going to do it one way for right now. Maybe we'll do the second one. What time is it? We got 19 minutes. We've been going for 19 minutes. I don't have 19 minutes left. We've been going for 19 minutes. I'm going to take angle C and D. And I know that these are consecutive interior angles because, this is still a parallelogram. And all the properties of a parallelogram still apply. So these would be consecutive interior angles. So that means I can put the measurement of angle C plus the measurement of angle D. That's going to equal 180 degrees. If I know that half of angle C is 61. That means the other half is also going to be 61. I could do 61 plus 61. That's going to be 122. Plus my measurement of D is equal to 180. Subtracting my 122, I'd get a measurement of angle D is equal to 58 degrees. Now, you may stop here and think, okay, 58 degrees is what the measurement angle 4 is going to be. No, that is not the answer. Because angle D is this whole angle right here, angle 4 is only half of it. So I have to divide angle D by 2, and then that will lead me to get my answer of 29 degrees. It's not too shabby. This is one way you could do this, or you can do it a second way, and I will use the second way in red. The second way deals with triangles. Looking at this triangle that angle 4 is in, I can see that I have angle 3 and angle 1 also in there. Maybe we can draw a picture that goes with it. What is the measurement of angle 3? I know angle 3 is 61, so I'm going to dot that and put 61. What's the measurement of angle 1? Is 90 degrees, and I don't know what this is. Let's just put D there. Remember that the sum of interior angles of a triangle is 180 degrees. So I could do D plus 90 plus 61 is equal to 180. And then solve for D. I'd end up getting 29. Another way to look at it, I didn't think of that way until someone in third hour said it, and I thought, hey, that's pretty clever. I didn't even think about triangles because I'm in chapter 7. But it's good to pull from past knowledge because, sometimes you don't even need to learn a new way. You can just use the old ways and it'd be easy. Almost done. Last theorem too, and it's the only one for rectangles. This being the rectangle diagonals theorem. It states that a parallelogram is a rectangle if and only if its diagonals are congruent. So that means ABCD is a rectangle if and only if AC is congruent to BD. With that knowledge, we can do example 2 and figure out what the length of both W and Y, or WY and XZ are, and see if they actually are diagonals, see if they are congruent with each other, and we can also find X. Giving a quick sketch of what this looks like, we have W, X, Y, Z, and then the two diagonals going across our rectangle right there. Since we're dealing with congruents and congruent segments, that means WY is going to be equal to XZ. So I can set 6x minus 7 equal to 3x plus 2 and start solving for x. I'm going to add my 7 over to get 6x is equal to 3x plus 9. Moving that up top. I'll subtract 3x first. And then I'd end up with 3x is equal to 9. Divide by 3. Now I end up with x is equal to 3. And now I can plug in this 3 to WY and XZ. WY, when I plug 3 in, I should get 11. And I would get the same for XZ, getting 11. So it's not too bad. Something we're kind of used to already. We've done similar problems with just congruent segments in the past, so it's not too bad. What is very new is example 3, where you may be given a set of coordinates, a set of points. You might have to graph it. In this example, I'm giving you the graph already with the points on it. But we got to decide if ABCD is a rectangle, rhombus, or a square. And we need to give all the names that apply to it. Now, when asked this loaded question, there's many different ways we can do this. I want you to prove as many names as possible. So that means for these problems, I want you to be doing both ways that I am showing you today. The first way we're going to do this is finding out if this is a rhombus or not. To find out that if this thing is a rhombus, we need to see if the diagonals are perpendicular. How are we going to see if the diagonals are perpendicular? Well, we're going to have to use the slope formula with that one. The other one is a rectangle. How are we going to figure out if this is a rectangle? Well, we need to know if the diagonals are congruent. And we're going to do the distance formula for that one. How are we going to know if this is a square? We know it's a square if it is a rhombus and rectangle, which is why we have to do both anyways to figure out if it's a square or not. So, yeah, it's required. Yeah, let's get started. Let's do the rhombus first. You could count the slope if you wanted. I am going to not count the slope. I want to do the math. So I'm going to write rhombus and I'm going to do my work under. So we're going to find the slope of AC. And remember, slope is y2 minus y1 over x2 minus x1. So I have 0 minus 6 over 4 minus negative 2. That is equal to 0 minus 6 is negative 6. 4 minus negative 2, making it pluses, that's over 6, and that's going to be negative 1. Okay, yep. For BD, I have that negative 2 minus 8 over negative 4 minus 6. That's going to give me what? Negative 10 over negative 10. And that's going to give me 1. Negative 1 and 1. These slopes are perpendicular with each other. So I can say that ABCD is a rhombus. But I can't stop there. I got to do the rectangle as well. So I need to find the distance from A to C. With the distance formula, remember the distance formula, that is the square root of y2 minus y1 squared plus x2 minus x1 squared, all under a square root. Doing the slope, doing the distance formula, I have 0 minus 6 squared plus 4 minus negative 2 squared, and I'm going to put it under the square root. I end up with negative 6 squared plus positive 6 squared. make those into positives under a square root, I'd end up with 36 plus 36 and have the square root of 72. I'm not going to find the real value of that because I don't have my calculator at home. I'm doing this just like straight up. These are different from what I have in my notes. So BD, I have negative 2 minus 8 squared plus negative 4 minus 6 squared. Let's see what we get. We have negative 2 minus 8. That is 10 squared. Well, negative 10 squared. And then plus negative 4 minus 6. Would that be negative 10 still? Negative 10 squared. That is equal to the square root of 100 plus 100. And that's equal to the square root of 200. These are not the same, or not congruent, so not a rectangle. So that means at the end of the day, so ABCD is only a rhombus. Yeah, you have to check. You have to do both because I have to know if this is a square or not. So you have to do the slope of the diagonals and find the distance of the diagonals. You have to do both. It just turns out in this case that it is only a rhombus. But if this so happened to be a rectangle as well, and I'd end up with a rectangle and a rhombus, then in green I would have wrote this is a square then, or like this is also a square because of these two. And then for my final statement, I'd say that ABCD is a rhombus, rectangle, and a square. I'd say all three of them. It's not too bad. The worst part about this section is probably the amount of talking I've had to do. But it is what it is. It's not too bad of a concept. Have fun on your homework.